Welcome to session 1 of week 1 problems. Problem number 6. Evaluate integral 0 to 2 pi d theta by 1 minus 2p cos theta plus p square. Here there is a condition given that p is a fixed real number in between 0 and 1. And let us take cos theta is equal to e raised to I theta plus e raised to minus I theta by 2. In order to do this problem, consider a contour mod z equal to 1, which is a circle. Hence, z is equal to e raised to I theta. dz is equal to e raised to I theta into I d theta. Therefore, d theta is dz by iz. Again, substituting z is equal to e raised to I theta, cos theta becomes z plus 1 by z by 2. Substituting these values and considering the closed contour mod z equal to 1, we get the integral I is equal to integral over c dz by iz into 1 minus p into z plus 1 by z plus p square. Rearranging, we get I equal to minus 1 by ip integral over c dz by z square minus z into 1 by p plus 1. Let us consider that roots are alpha and beta. So alpha beta should be 1 and alpha plus beta should be equal to 1 by p plus p. So alpha is p and beta is equal to 1 by p. Since p is less than 1, z is equal to p is a pole inside the contour, while z is equal to 1 by p is outside the contour. So let us find the residue at z equal to p. So residue at z tending to p, z minus p f of z gives a value p by p square minus 1. So the value of the integral is equal to minus 1 by ip into 2 pi I into sum of residues of those poles inside the contour, which gives the answer 2 pi by 1 minus p square. Now let's move on to the next problem from classical mechanics. Again, this is a question of 2015 December CSR exam. The Lagrangian of the system is given by L is equal to half m q dot square plus 2m q2 dot square minus k into 5 by 4 q1 square plus 2 q2 dot q2 square minus 2 q1 q2, where m and k are positive constants. The frequency of its normal modes are. So such problems are possibilities in CSR exams. So in order to solve normal modes of vibration, we write L is equal to T minus V. And we take T as the kinetic energy matrix and V as the potential energy matrix. So comparing with the Lagrangian, we get T is equal to a 2 by 2 matrix given by m by 2 0, 0 to m, V equal to 5 k into 5 by 4 minus 1 2. So in order to find the frequencies of the normal mode, we find the value of the secular determinant t omega square minus v. So substituting those in the equation and solving, we get a quadratic equation given by m square omega raised to 4 minus 7 by 2 km omega square plus 3 by 2 k square is equal to 0. Rearranging, we get omega raised to 4 minus 7k by 2m omega square plus 3k square by 2m equal to 0. So the roots are root of k by 2m and root of 3k by m. So this is the normal modes of vibration of such a system. Now coming to problem number 8. This question is asked from the topic electrodynamics, where a uniform field magnetic field is given, B is equal to V0k, where B0 is a constant. The question is, what is the possible choice of the magnetic vector potential A? We know B is equal to del cross A. So this del cross A should be is equal to V0k. So substituting the values of given the choice, we find that the second choice, that is A is equal to minus B0yi, yields the answer V0k. Hence the answer B. Now another question from mathematical physics, again asked in 2015 December CSR exam. It comes in part C. The Hermite polynomial Hnx satisfies d square Hn by dx square minus 2x dHn by dx plus 2n Hn is equal to 0. So this is actually the Hermite differential equation. Now the generating function is given, that is g is equal to sigma Hn by n factorial t raised to n. We are asked to find which of the following condition is satisfied. So in order to find that, let us first find out d square g by dx square. So since we are differentiating with respect to x, Hn changes to Hn double prime x. Now dg by dx yields sigma Hn prime by n factorial t raised to n. And dg by dt gives Hn by n factorial into n into t raised to n minus 1, since differentiation is with respect to t. Substituting the values in the relation, we find that sigma Hn double prime by n factorial t raised to n minus 2x Hn prime by n factorial t raised to n plus 2t sigma Hn by n factorial n t raised to n minus 1 is equal to 0. Equating the coefficient of t raised to n, we get Hn double prime by n factorial minus 2x Hn prime by n factorial plus 2n Hn by n factorial equal to 0, and multiplying throughout by n factorial, we get the Hermite differential equation. Hence the answer is definitely A. Now coming to the last question, which is actually a question based on random walk motion. Consider a random walk on a square lattice. At each step, the walker moves to the nearest neighbor site with equal probability for each of the 4 sites. The walker starts at origin, takes 3 steps. The probability that this walk no site is visited more than once is. To do that, let us consider a square lattice. The first step, that is the blue one which is shown in the figure, is purely random. Next step shouldn't retrace the blue path. So probability that the green path does not retrace the blue path is 3 by 4. Now next is the orange step, and the condition is that the orange step shouldn't retrace the green path. So probability that the orange path doesn't retrace the green path is again 3 by 4. Since we are considering dependent events, the total probability will be 3 by 4 into 3 by 4, 9 by 16. That is the answer. Thank you for patiently listening. The lecture will continue next week also. Thank you.